All right, so now let's talk about how we treat planes within these crystal lattices. So they're treated somewhat differently than points and directions, and you saw the clear similarities between points and directions because they both use the values of a position vector, so you can think about it as a point or a direction in both cases relative to the origin. But however, we treat planes in a different way, and this has some ramifications that make it easy, or have some implications for how we read planes and how we compare and contrast their indices as well. So we still define an origin. So that's still important. But after defining origin, what we do is express the orientation of the plane we're interested in, so plane in space, relative to the crystallographic axes. And so these are, X, Y, and Z, right? So we're relating these crystallographic axes, or sorry, we're relating the orientation to those planes. And so particularly, we describe the distances from the origin, at which point the plane, so we have a plane that intersects a given axis. So let me sort of draw that for you, and we'll go through an example. So again, let's imagine I have a Cartesian coordinate system, x, y, and z, and that defines my unit cell, right? So this would be my I would have a certain a vector, I would have a certain b vector, so a, and then this would be b, and then I'd have a certain z vector along that would be the c direction, and so I would define a lattice in that way. So like this. So that's my lattice composed of an a vector along the x direction, b vector along the y direction, and z direction. So you can define the, so I'm using Cartesian coordinates, but it could very easily just be other angles and so forth. So if I'm interested in a certain plane, right, so this plane over here, right, so it extends infinitely, but we're just going to draw this shaded region to indicate that on the unit cell, right? So again, what we're looking for is the intercepts of the plane with those three axes. And I draw it as x, y, and z, but we could just as easily, have it, if it's a non-Cartesian axis for other systems, it could be non-90 degree and so forth. But that's what we're going to do. So we're looking for the intercepts of this plane with the various axes that we have. And this point I defined as my origin O. Right? So we have to have an origin, our coordinate system with A, B, and C. And so then what I'm going to do is, for me, this is a personal preference, but what I like to do is make a little table. So my directions, which I'm going to, in this case, attribute to X, Y, and Z, but it could be A, B, and C. This is just for convenience. What I'm going to look at is, I'm going to make this table, and the first thing I want to look at is the intercepts. And so specifically with this as my origin, and again, this choice of origin was somewhat arbitrary, but I'm going to stick with it for this case. I'm going to look at my x-axis, right? And I'm going to look at the intercept of this plane with the x-axis, starting at the origin. And so if this runs along this direction, and this plane continues in all directions, then you'll see that this is parallel to the x direction, the x-axis. And so these do not intercept. So you're never going to have an intercept in that case. And so typically, I'll define that as infinity. That's how I would kind of write it in these cases. So I'm going to write infinity for any time it doesn't intercept. All right, so let's go to the next one. Starting at the origin, looking at the intercept of that plane with the y-axis, you can see that my plane here intercepts the y-axis at the corner here. Well, that is a one value of b, right? So this is the b vector, right? And it's one unit of that because it's the unit cell. And so I'm going to put 1. So basically, if you want to think about this in more descriptive terms, it's one integer times the b vector. All right, then I go on to the next one. And the z-axis, again, we see that if this plane runs infinitely in all directions, we'll see that it again is parallel to both. It's parallel to the xz plane, and so it's going to by definition be parallel to the z direction, and so we have another does not intercept, and so we have infinity here. So those are my intercepts: infinity, 1 times the b vector, and infinity. So we can use this to describe the plane. And so the way we do this is by taking the reciprocals of each of these intercepts. And I'll show you this in a second why we do this, but we take the reciprocal. So 1 over infinity, we define that as 0. And then 1 over 1, so that's going to be 1. And then 1 over infinity again is going to be 0. So our reciprocals are 0, 1, and 0. And so these are what we call Miller indices. 0, 1, and 0. And so this is how we define, or if we generalize now, this would be H, K, and L, and we use it inside of these parentheses. And that's our convention for writing planes. All right, so we have the Miller indices generally H, K, and L in these parentheses, and for the plane that we were talking about, 0, 1, 0. So the Miller indices are these values, and those are defined for planes as the reciprocals of those intercepts that we talked about. So I want to give some other kind of notes, just like we did with directions, that kind of illustrate how we define planes and sort of the nomenclature or the way that we describe them to communicate to other people. So again, parentheses, that represents a plane. So again, if I just see the parentheses, I know it's a plane. If I see the square brackets, I know it's a direction. And convention says no commas. So you'll see in the indices, I didn't put commas in between these. It's just assumed that we know the distinction there. And again, H, K, and L are Miller indices. So we called the indices for directions just indices. We add Miller when we're talking about a plane. So it's basically a scientist that worked on planes, and so we give that person some credit, and that's why we call them Miller indices. So it's, again, if you just hear Miller indices, you're thinking planes. And just like directions, we tend to avoid, we try to use the smallest integers, and so it shouldn't have, should not contain fractions. So as a general rule, we don't want to have fractions. So we'll typically multiply by a common factor to achieve an integer. And then same way, if we have negative numbers, we represent that with a bar over that number, and we say it the same thing. So a bar over the indices. All right. So I was kind of careful not to mention that we want to avoid fractions here in planes, but it's not exactly the same as directions in that we had, for example, if we had a point and direction 1, 0, 0, which is the same as 2, 0, 0 because the magnitude doesn't matter, right? So we got the smallest integer. But in planes, if we have the same example, so if I have a plane that is 1, 0, 0, it has those indices, Miller indices, and I compare that to a 2, 0, 0, they are not necessarily the same thing. So these two are not the same. So let me draw you and kind of hopefully prove to you that that's the case. So if I'm looking at, and this 1, 0, 0 is going to be very similar to what we looked at up here with the 0, 1, 0. So it's just slightly different. So let me show you this. So I've got a basic unit cell here. And if I look at the 1, 0, 0 type, a plane, it's going to be one of these faces on the cube. So this one. And then another one's going to be over here. And they're have a spacing of what we call D1, 0, 0. So the spacing between these planes is 1, 0, 0. Well, if I draw a similar unit cell, and I want to look at the 2, 0, 0 type, well, I'll have 1, 2, 0, 0 type plane that's right here, but I'll also have one that's kind of in the middle of this unit cell, and then I'll have another one that's over here. And so the spacing between these is D for spacing, and then 2, 0, 0. So they are parallel to each other, right? Both of these are parallel, and they contain similar, but the spacing between consecutive planes is smaller. So this is going to come into play when we start looking at diffraction with these types of planes. So the a 2, 0, 0 and a 1, 0, 0 tell us a little bit more information. That it can refer to this half plane with the 2, 0, 0. So that's an important distinction to make. And so we aren't necessarily going to try to achieve the smallest integers when talking about planes, like we did in directions. All right, and then last note on this, just like we did for directions, we have families of directions. All right, for another note I want to bring up is for the cubic system. And so this doesn't apply to the other systems, but let's say I have a direction, and again, square brackets here, HKL, right? And I want to look at the plane, and I want to look at a plane with the same indices, right? So I have a direction with the indices HKL. I have a plane with those same indices HKL. And so that could, for example, be looking at 1, 1, 1 and 1, 1, 1. So the important thing here for the cubic system is that these will always be perpendicular. So this is going to be perpendicular to HKL. So that's kind of an important distinction. And you might, and this is part of the reason why we choose to represent planes in the way we do. So that if we're talking about this relationship, we know that these planes are perpendicular to the direction in cubic space. So let me sort of draw you an example of this. So I have a cubic lattice. This is X, this is Y, this is Z. If I draw the 1, 1, 1 plane first, I'll draw that one first, and that forms this triangle. It's a diagonal through the cube. And if I draw the direction, we kind of already saw this, I showed this example, but that starts at the origin and goes to this diagonal point. Right? And so again, you can show that these are perpendicular. The plane and this direction are perpendicular to each other in this cubic space. All right. The last comment I want to make here about planes is that we talk about these Miller indices. And I showed the example previously with relation to this spacing. So this is going to become really important in X-ray diffraction when we talk about that. So the spacing here between adjacent planes and the spacing here, right? So the last comment I have is that these Miller indices excuse me, are useful for determining relative interplanar spacings. So interplanar is that D spacing we talked about. So the spacing between equivalent planes. So the relative conclusion we can come up with is if we have low Miller indices, this gives us large interplanar spacings. And if we have high Miller indices, this means smaller interplanar spacings. So low numbers give us higher spacing, higher Miller indices give us smaller. So again, going back to that previous example I showed you, the same can be true here, right? I'm looking at 1, 0, 0, relatively low Miller indices. That gives us a larger spacing than a higher number, which gives me smaller spacings. So that rule follows through for other types of Miller indices, not just these 1, 0, 0, 2, 0, 0. The relative spacings apply onward. All right, another distinction of this difference between Miller indices, where the smaller the numbers are, the larger the spacing. So this is a two-dimensional lattice, so there's only two indices. But if you look at 1, 0, that's relatively large spacing. 1, 1, you can see that the spacing is a little smaller. 2, 1, still smaller. 1, 3, smaller, and then 4, bar 1, even smaller, right? So that's still the connection. And so the smaller the numbers, the larger the spacing. The larger the numbers of Miller indices, the smaller the spacing. So I might have said that backwards. So let me repeat that. The smaller the Miller indices, the larger the spacing. The larger the Miller indices are, the smaller that spacing is. So that's kind of a visualization of this trend.